Greetings, pre-calculus students, to another day in our unit on sequences. Today we're actually going to be starting a new major topic, which is this idea of series. Our first major topic were sequences. Now we're going to talk about this idea of series. And you'll see by looking at these objectives, a major part of what series are is this idea of finding the sum. Finding the sum, or adding up a bunch of terms or numbers to find a result, okay? And then you will also be introduced to a new notation, namely sigma notation, that you might have seen before, but most likely you haven't. So this might be your first exposure to said notation. But first, before we get to it, let's quickly talk about the bell ringer, just in case it was not covered in class. Obviously, if you answered the bell ringer correctly, you can skip this part, but if you didn't, then probably a good idea to make sure you pay attention to these next couple minutes of the video. So find an explicit formula for the following two sequences. So number one, 20, 17, 14, 11, and 8. So hopefully you can see that this is clearly arithmetic because all we are doing is just subtracting 3 to get from one term to the next. Or in other words, the common difference is negative 3. So we have a sub n is equal to negative 3n plus c. So from there we have to find the c value, which if you remember, the c value is the zero term, a sub 0. What is the zero term of this sequence? Or in other words, what is the term before 20? Right, what is the term before 20? Well, if the common difference is minus 3, that means the term before 20 would have to be 23. Because if you were going backwards, that means instead of subtracting 3, you would add 3. So 20 plus 3 would be 23. So that means our c value is 23. So a sub n is equal to negative 3n plus 23. That is your explicit formula for number one. Now let's look at number two. The sequence that might not seem obvious what it is, but especially if you look at the fractions, but if you look at the whole numbers, you would see that this is geometric because there is a common ratio this time around of multiplying by 4 to go from one term to the next. And even with the fractions, you could maybe see that as multiplication by 4 because 1/4 is the same thing as 4 over 16. So it would make sense to go from 1/16 to 4/16. You would multiply it by 4, or you would multiply the numerator by 4. So hence common ratio. So hence the explicit formula, at least at this point, would be b sub n is equal to b sub 0. Actually, that's a little bit messy. B sub 0 times the common ratio 4 to the n power. So now we just have to figure out what the zero term is. Well, if the first term is 1/16, we have to figure out what the term before that would be. Well, once again, the common ratio is 4, so that means if I went backwards, I would divide by 4, right? If I went backwards, I would divide by 4. So the zero term, sorry, again, I messed up with that B. The zero term for this sequence would be 1/16 divided by 4, which is the same thing, sorry about that, same thing as 1/16 times 1 over 4, which is 1/64. So that is the zero term, 1/64. So our explicit formula is b sub n is equal to 1/64 times 4 to the n power. Excuse me. So once again, that was just a quick run through just in case the bell ringer was not covered in class. But like I said, if you answered both of these correctly, hopefully you skipped this part of the video. All right, so let's get to today's lesson. So once again, we're starting on a new major topic in this unit, which is this idea of series. So one thing that we're going to do a lot of this next, let's say 2 weeks or so, is we're going to look at this idea of taking a sequence and finding the sum of its terms. All right, so taking a sequence and finding the sum of its terms. So literally just taking the numbers in the list and adding them up, okay? And to do that, one way we make it a little bit easier for us, one way to make it a little bit easier, a little bit convenient to us is using a new notation that once again will most likely be new. So this notation is called summation notation or sigma notation. So it's called summation notation because, once again, we're literally finding the sum of a sequence of numbers. And sigma notation because it utilizes the Greek letter sigma, which, as you can see here, kind of looks like a capital E, kind of. But once again, this is the Greek letter sigma. And this is what the notation looks like. Okay, so you have your sigma, and then you have on the bottom of it, I is equal to 1, the top of it, n, and then the expression a sub I. So the way you would read this, you would say the sum of a sub I from I is equal to 1 to n. So let's break this down a little bit. So as soon as you see the sigma symbol, you immediately should think, I'm finding the sum of a list of numbers. I'm finding the sum of a list of numbers. That's the first thing. So now let's talk about this I is equal to 1. Well, this I is equal to 1 is basically telling you start with 1. Start with 1. That is the first number that we are plugging into our expression. Another name for this is called the lower limit, because that is the lowest, that is as low as we go in terms of our integers. We don't go any lower than 1 in terms of what we're plugging in. The number on top, so this n would actually be some integer. It wouldn't be just a variable, though it could be. It would be some integer. So this would be finish with whatever n is, and this is called the upper limit because we don't go any higher than this integer. So if the integer was 5, we wouldn't go to 6. No, we would just stop at 5. And then a sub I, that's where you're plugging in your numbers. That's where you're plugging in your start all the way up to your finish. Okay, so you would plug in 1 and so on and so forth. So let's do an example. So example 1. Evaluate the following expression. The sum of 3i from I is equal to 1 to 5. The sum of 3i from I is equal to 1 to 5. So once again, we start with 1 because that's what it's telling us. It's telling us to start with 1. So that means our first term would be 3 times 1. Okay, 3 times 1. Well, what would be our second term? Or what would be the second number that we plug in? Well, this is where we're going to fill in some details. So we start at 1. We know we're finishing at 5. But basically, you're going to be doing all the integers in between. So all the integers starting at 1 all the way to 5. So 1, 2, 3, 4, 5. All right. So now we got to do 2. And once again, we're finding the sum of all these terms. So that's why I put that plus sign there. We're finding the sum of all these terms. So plus 3 times 2. Because we already plugged in 1. Now let's plug in 2. Because the next integer after 1 would be 2. And then 3 times 3. 3 times 4. Before finally finishing up with 3 times 5. Because we don't go to 6. Because we're told that our upper limit is 5. So we finish at 5. Okay? So once again, as you can see here, the only thing that changed was the I value, which hopefully makes sense, right? Because the I value is your variable. So that is the only thing that should be changing. The 3 in front should not change because it's just a 3. So that should, as you can see, that the 3 in front was always there for each term. The only thing that changed was the I. I was 1, then it was 2, then it was 3, then it was 4, then it was 5. So once again, all the integers starting at 1 all the way up to 5. So you got to make sure you do the integers in between as well. And that's it. Now we just quickly calculate what is our final answer. So we got 3, then 6, then 9, then 12, then 15. So what is that? So that's 18, 30, 45. 45 would be our sum. 45 would be our sum. And that's all you're doing. That is all you're doing. Okay? So once again, starting here all the way up to here. Okay? And then, yes, do all the integers in between as well. So this first checkpoint is going to be your first on your own problem. So this first checkpoint is going to be your first on your own problem. okay? And you're basically just doing what we did in the previous example. This time, though, you're starting at 3, as you can see. You're starting at 3, so that's the first number you plug in for I, and then 4, then 5, and then finally 6 would be the last number you plug in for I. And then, like I said, you're adding up all these when all is said and done. You're adding up all these when all is said and done. So that's your first on your own problem. All right, now let's talk about going backwards. So let's say you're given a sum, and I ask you, tell me what this looks like in using summation notation, using sigma notation. So I'm basically asking you, what does this sum look like if I wrote it like this, using this notation? Well, let's see. Let's start with the expression first. So the expression. So like what goes here? Well, let's see. What's staying the same? Let's see. There's always a 1. Okay, so there's always a 1 for each of the terms. It looks like there's always a 3, right? There's always a 3. And then it looks like the only thing that changes is the number next to 3, or the number being multiplied by 3. So the number being multiplied by 3 changes, or it varies. It varies because that means there is a variable next to 3. There is a variable next to 3, and we'll call it n. You can call it anything you want. You can call it x. In the previous example, you saw that it was I. You can use any variable letter you want. I'm going to use n. So once again, it looks like there is a number next to 3 because the number varies from term to term. So that means there's a variable if it varies. So that's our expression. But now we have to figure out, okay, where do I start? Where do I start and where do I end? Well, let's look back at the series. It looks like the first number next to 3, right, which is our variable, the first number next to 3 is 1. So it looks like we start with 1. And it looks like the last number next to 3 is 9. So it looks like we end with 9. So that would be our answer for this sum. Okay, so we're not solving this. We're not calculating what the sum is equal to. We're basically just saying, what would this sum look like if I wrote it using this notation? Okay, so once again, you're just working backwards. And that would be it. Now let's look at one more problem together. Checkpoint 2. Now, normally I would have you do this on your own, but I actually want to do this. I want us to do this together. So we have 3, 5, 7, 9, 11. 3, 5, 7, 9, 11. So we have to figure out, once again, we have to figure out what this looks like using this notation. We have to figure out what this looks like using this notation. So 3, 5, 7, 9, 11. All right. So this one might be tricky because it looks like the number always changes. So is that our variable? Well, not exactly. We have to use the knowledge that we gained from the previous section of our unit, which is this idea of sequences. So if you just ignore the fact that this is a series, that this is a sum, if you just look at the terms, so 3, 5, 7, 9, 11. What kind of sequence is that? 3, 5, 7, 9, 11. If you said arithmetic, you would be correct. That is an arithmetic sequence because to go from one term to the next, there is a common difference of 2 between consecutive terms. So that means if I were writing an explicit formula, I would have 2n plus c so far. Now, obviously, we still need to figure out what the c value is. And just like we talked about in the bell ringer, the c value is just the 0 term. Well, what would be the number before 3? If I went backwards? Well, the number before 3 would be 1, right? Because if I'm going backwards, that means I'm subtracting 2. So I would subtract 2 from 3 and I would get 1. So the 0 term seems to be 1. So our explicit formula is 2n plus 1. Well, why is that helpful? That is our expression. That is what we are taking the sum of. We're taking the sum of 2n plus 1. Where do we start? Well, now we have to think about it a little bit. So what would be the first number we plug in? So once again, I used n here, but you can use any variable you want. You don't have to use n here. Like I said, you can use x or I, whatever. Well, remember, if this is what we're using, 2n plus 1, and if I want 3, well, we assumed, when we made this formula, we assumed 3 was the first term. Okay, that's the assumption that we made. And it's not a wrong assumption because it was the first number, so that would be the first term. So that means we start at 1. We start at 1. Now, we can easily test this. If I plug in 1 into this expression, what do I get? Well, I get 2 times 1 plus 1. 2 times 1 is 2 plus 1 is 3. So that checks out. Okay? So it's not always going to be 1, though. In a lot of cases, it will be 1, but it won't always be 1. It's 1 in this case because when we found this formula, we assumed that 3 was the first term. Well, what about 11? Well, if 3 is the first term, 2, 3, 4, that means 11 is the fifth term, right? 11 is the fifth term. So that means that's the last value for n we would plug in. And once again, we can easily test it. If I plug in 5, I get 2 times 5 plus 1. Well, 2 times 5 is 10 plus 1 is 11, so that does work. So that means this sum would be represented by this series. The sum of 2n plus 1 from n is equal to 1 to 5. Okay? So I wanted to do that one together because it might not have seemed obvious that you had to identify it as an arithmetic sequence so you can figure out what the expression is that we put into the sigma notation. So that's checkpoint 2. So we're going to do one last slide of just simple definitions here. So the sum of the terms of a sequence is called a series. Okay, so if you take a sequence of numbers and you add them all up, that is a series. The sum of the first n terms of a sequence is called a finite series and is denoted by the following notation. So if you want like the first 5 terms or the first 10 terms, so on and so forth, okay, that would be a finite series, okay? Because it would make sense. You're starting at the first term, you're going all the way up to 5 or 10 or 15, whatever. Now, there is another type of series, an infinite series. So the sum of all the terms of an infinite sequence is called an infinite series and is denoted by this. So you'll see, instead of just taking the first 5 terms or the first 10 terms or whatever, we're going to take all the terms to infinity. Okay? So you'll see why, yeah, there's no finish to this series. It just keeps on going. If you're at the 1,000th term, I got to find the 1,001st term, so on and so forth. So you're just going to keep on going, finding all the terms, adding them all up indefinitely. This one is, we will initially focus on the finite series. The infinite series is something that we're going to talk about later on. Okay, so we're gonna focus initially on these finite series, and then later on we'll talk about this idea of infinite series. All right, and then the rest is going to be on your own problems for this lesson. So for the first 2 is just finding the sum. Once again, take note of where you start, where you finish, and remember you're doing all the integers starting here all the way up to here. So for the first one, it would be 1, 2, 3, 4, 5. You would be plugging in for I. So that's 1 and 2. Same thing goes for 3 and 4. Okay, you're just finding the sum. Once again, pay close attention to where you're starting. So for these 2, you'd be starting at 0, not at 1. So the first number you would plug in would be 0, not 1 this time around. And then for 5 and 6, these 2 problems would be similar to example 2, where you have to figure out what this looks like in sigma notation. Whoops. Okay. So 5 and 6 would be very similar to, once again, example 2. And then 7 and 8, same thing, but these ones are more similar to checkpoint 2. Because for these ones, you're going to have to ask yourself, is this arithmetic? Is this geometric? And then use the explicit formula as your expression in the sigma notation. All right. That is it for today's lesson. As usual, if you have any questions, let me know. Feel free to ask me during class, outside of class, through email, whatever you feel most comfortable with. Otherwise, I hope this lesson went well. Hope you stay safe. And I'll see you guys in the next video. See you later.